Hi, this video goes over the AVL tree Trinode Restructuring operation. This is what restores balance in an AVL tree after an insert or remove. This is based directly on the previous video about AVL trees, so make sure you've watched that video before this one. Let's recap the problem that we're trying to solve. When we insert or erase a pair into an AVL tree, it can unbalance that tree. Namely, it can increase a balance factor from 1 to 2. AVL trees allow balance factors of only 0 or 1, so inserting or erasing a node changes heights, and that can increment a balance factor from 1, which would be legal, to 2, which is illegal. We've claimed that an insert operation can only unbalance one node between the leaf that we created in the root, and an erase can unbalance multiple nodes. So what we need is a trinode restructuring operation, or that's what it's called, and what it does is it repairs the balance among one unbalanced parent and its immediate descendants. The trinode restructure operation, it's this local thing that just looks at one node that's imbalanced and kind of the children of that node, that immediate neighborhood, and restores the balance factor in that one spot. In the case of insert, that would rebalance the entire tree because after an insert, there can only be one imbalanced node. In the case of erase, you have to look for multiple locations where there's imbalance, but every time you find one, this trinode restructuring operation will fix it. The trinode restructuring operation is a constant time thing because it looks at big O of 1 nodes, and it takes big O of 1 time to just rearrange them into different locations. Before we get into how it works, I want to make one point, which is that an unbalanced node is always a grandparent, meaning it has a child, and then below that there's another child level. It could be even higher than that, but we know there's at least 2 nodes deep. So a node at height 0 is always balanced because a node at height 0 has no children, so the balance factor has to be 0. A node at height 1 is always balanced according to the AVL invariant because a node at height 1 could have 2 children that are leaves, which would be perfectly balanced with a factor of 0, or a node at height 1 could have 1 child on one side, nothing on the other. That's a balance factor of 1, and that counts as balanced. But a node at height 2 may be balanced. It might be balanced, it might not be, because it is possible to make an unbalanced height 2 tree with 3 nodes in a row. So that means that if node Z is unbalanced, we know that Z is a grandparent, meaning that if a node has a balance factor of 2 or more, it has to be high enough so that there are at least 2 nodes below it. It's just not possible to create imbalance with a shorter tree than that. So here's kind of an illustration of this. A one high tree is always balanced according to AVL because there's no imbalance at all. A height 1 tree could be a little bit imbalanced with a factor of 1, but that's still okay according to AVL rules. It's only when you have height 3, or height 2, I guess, the way we count it, but 3 nodes in a row that you can get a balance factor of 2 that would need to be fixed to be an AVL tree. So keep that in mind. So here it is. Here's the pseudocode for the trinode restructuring operation. It's actually not that hard to do. It's a little bit wordy to define. So the input to this is an unbalanced grandparent node Z. So we're going to call Z the node where we notice the imbalance. Over here, that would be the root. It's a node with a balance factor of 2 is Z. And the goal is that the subtree rooted at Z is balanced. So to begin with, we've got a part of the tree that's imbalanced with a factor of 2, and we're going to move some stuff around and end up with every node having a balance factor of 0 or 1, which counts as balanced for AVL purposes. So first, we're just going to give some names to the nodes that are involved. Let Y be the child of Z of higher height. So we know that if Z is imbalanced, then its 2 children have to have different heights. That's what imbalance means. So Y is the higher of the 2. And then let X be the child of Y of higher height. It's the same thing. If we have a balance factor of 2 at grandparent Z, then Z's child Y has to be higher than its sibling, than Y's sibling. And Y's child X has to be higher than X's sibling, because that's the only way you can get up to a balance factor of 2. So we're just giving names to the 3 nodes in a row that are causing the problem. In this example with 3 nodes, Z would be the root, Y would be the child of that, X would be the child of that. Okay, then what we do is rearrange them in order, or increasing order by key. So we had X, Y, and Z. We don't know if X, Y, and Z go left or right, zigzag, left, right, whatever. There's a lot of different ways that can be shaped. So what we do is say A is the first node of x, y, z, meaning the one with the least key. We go in increasing order. B would be the middle key. C would be the node with the highest key. So now we're done with x, y, and z. We're going to forget about the names x, y, and z. From here on out, we deal with a, b, and c. Then what we do is look at the 4 subtrees of x, y, and z. So these are the 4 subtrees that aren't a, b, and c. So a, b, and c are going to have some left and right children. Some of the left and right children are B and C and A, right? But then there's other children we haven't accounted for. We call those T0, T1, T2, T3 for the 4 trees that can be hanging off of these 3 nodes, aside from the nodes themselves. So now what we do is replace the subtree rooted at Z with a new subtree rooted at B. So beforehand, Z was the parent, and this was causing a imbalance situation. What we want to do is move toward balance. So we want the middle value to be the root, not this extreme value. So if A, B, and C are in order, then B is the median value. It's the middle. So B is going to be the new root instead of Z. And then what we have to do is just put the rest of the tree back together again. So A has to be the left child of B because A comes before B in order. And then T0 and T1 are the 2 smaller trees that need to be attached somehow, and those are the 2 children of B. Finally, C is the other node that we have to reassemble. We make that the right child of B. And then T2 and T3 are the 2 remaining subtrees that need to be reattached, and those become the 2 children of C. Okay, I think an example will help here. So let's do one example. Let's use this example from before and see how this works. So this was a tree that was close to being an AVL tree, except it has one balance invariant violation at this node here, because the balance factor there is 2. So Z is the name of the node that has the balance factor 2 that's imbalanced. So Z is where we begin this. And then Y is the child of Z of higher height. So Z has a left child of height 1 and a right child, which is a null pointer, which is -1. So definitely the left child is the higher of the 2. So that's Y. And then X is the child of Y. It's the grandchild of Z of higher height. Y has a left child node of height 0 and a right null pointer of height 1. So X will be picked. The left child will be picked as X. So now I've got my X, Y, Z. These are kind of the important nodes that need to be rearranged. We're going to relabel them A, B, and C. So in this case, since Y is the left child of Z, we know that Y has to have a key less than Z due to the binary search tree invariant. Similarly, X has to have a smaller key than Y due to the invariant. So in order, it would go X, Y, Z. Another way of doing this is let's do the Euler tour. And what order do we hit these? Euler tour in order hits these on the underside, so it would go X, Y, Z. So it's X, Y, Z in order. So now we're going to relabel these A, B, C. So A is the first node with the least key, B, and then C. The T0 would be the left child of A, T1 would be the right child of A, T2 would be the right child of B, T3 is the right child of C. In this example, they're all null, but still we need to reassemble the tree appropriately. So the next step is replace the subtree rooted at Z with a new subtree rooted at B. So instead of having C or Z be the grandparent, what used to be called Z, we're going to make B the top of this part of the tree. So take these apart. We're going to put them together back like that. So now B is going to be the root. Notice that we've achieved better balance, and that's not a coincidence. That's the whole point of this operation. So this is a better balanced neighborhood. Before we had this kind of situation, which is left heavy. Now we've got a nicely balanced region. And then we just have to put it all back together again. So the null pointers that we gathered earlier, T0 goes to the left of A, T1 goes to the right of A, T2 goes to the left of C, T3 goes to the right of C, and then we reattach it back into the tree. And in this example, that worked because now this whole region has balance factor 0. That means the balance factor at the root is 1 because it's a height 1 on the left, height 2 on the right. So we've restored balance to this tree. And that's not a coincidence. This always works that way. Okay, so let's kind of see why this works and see how you can visualize the different cases of what can happen here. There's actually 4 different shapes that can happen before and after one of these restructurings. So remember that the 3 offending nodes, meaning the nodes where the imbalance is happening, kind of the action spot, we call them X, Y, Z. We relabel them to A, B, and C in order. So there are 4 shapes that these 3 unbalanced nodes can have. When you have the restriction that it has to go A, B, and C in order, Z is a grandparent, Y is the child of Z, and X is the grandchild of Z. There's only 4 shapes that can happen if we have an unbalanced situation. And the pseudocode kind of has four different cases. It's written to not have any if-else statements, which I think is a virtue of this. It's pretty simple to understand and execute, but there's four different before and after kind of pictures we can get. We're going to look at pictures of them. I'm going to call the four cases A, B, C, D, and observe as we go through these that every case moves a subtree that is too high relative to its sibling closer to the root. So the reason why an imbalance happens is because in this neighborhood of A, B, and C and its descendants, one of those subtrees is too high relative to its sibling. That's what's causing the imbalance problem. And in every case, this restructuring moves that closer to the root to be on a level with a sibling that's higher so that the imbalance goes away. So here's case A. We've done some color coding to try to make this easier to follow. So this is one of the four shapes that A, B, and C could have. The situation here is where when we go from the grandparent down to the child, we go right twice. So you could call this right. And if we have A, B, and C, what the Trinode restructuring algorithm will do is always make B become the root of the tree and then hang off the T0 through T3 in the places they have to go. We've used a color code for the subtrees. This green is good. It's a balanced subtree, but the red subtree is too high relative to its siblings. So in this case, it would have been T2 right here that's causing the problem. Notice to begin with that if we start from the grandparent, we have to go down 2 levels and then to T2. So there are 3 edges between T2 and the root, and that's the problem. It's too high relative to T3. But now, after this rotation, now there are only 2 edges between T2 and the root. So T2 is too high, there's too many nodes there, and this restructuring has the effect of moving T2 upwards, closer to the root, and that's what resolves the imbalance problem. Okay, the other 3 cases all have a similar pattern, they just have different shapes. So what we're going to call case B is when you go from the grandparent down to the grandchild, you go left twice. So A was right and then right. B is left and then left. The subtree that would be causing the problem here would be T1. Again, there is 1, 2, 3 edges between T1 and the root of this neighborhood of the tree. After we do the restructuring, there's only 1, 2 edges between the red too high tree and the root of this region. So again, that's what resolves this balance factor problem. T1 was 2 units too high relative to its neighborhood, and when we move it 1 level closer to the root, that makes it balanced enough. Okay, C and D have the same kind of a thing. In the case of C, the path from the grandparent to the child is a right and then a left. So far we've seen left, left, we've seen right, right. Now we're seeing right, left. You might have noticed a pattern here. There's 4 of them. There's 4 ways you can do this. The other alternative is left and then right. You know, we have 2 binary choices, and so there's 2 times 2 makes 4 different cases. So in case C, the path from grandparent to grandchild is right and then left. We've got A, B, and C color-coded there, and B is always the one, the median value in the middle always becomes the root, and then we hang A to the left of that, C to the right of that, and then hang the 4 subtrees in the only place they can go according to binary search tree invariant. Same thing, red T1 was 3 edges from the root of the subtree. Now that red subtree is 2 edges away from the root. Finally, D is the only other possible alternative. From grandparent to grandchild is a left and then a right, and the same kind of restructuring happens. Let's do a quick analysis of the restructuring itself. A single trinode restructuring operation takes constant time. If we go back and look at the pseudocode, there's no loops or recursion going on here. It's just a bunch of assignments. We create these variables x, y, z. We have some if statements to decide which is which, but there's no loop or recursion. It's kind of complicated, to be fair, but it is big O of 1 time because there's no repetition going on. So even though it's a relatively lengthy constant time operation, it still counts as big O of 1. So how does that factor into the entire insert or erase operation? So AVL insert, we've said, does at most one of these restructurings. So the entire AVL insert process would first search for, or the rebalancing process would search for an unbalanced node. That takes big O of h time to start at the leaf, work our way back up. We do 1 restructuring that takes constant time. So it's a total of big O of 1 plus big O of h time. It's big O of h time to do the whole rebalancing operation. Erase is a similar situation. Erase can do up to big O of h restructurings because it's possible that there have to be multiple trinode restructures on that path from the leaf to the root. but there's at most h of those if h is the height of the tree. And that loop takes big O of h time to find them. So we do big O of h restructurings. Each one takes constant time, so we spend big O of h time in the Trinode Restructure function and a total of big O of h time restructuring. So in both of these cases, the total time it takes to rebalance an AVL tree after an insert or erase is only big O of h, and if we can make the height of the tree small, then this is a fast operation.